I'd like to first thank Rick for accommodating me, even though I blew the deadline by a mile, and being able to squeeze my talk into the program. I'd like to tell you a little bit about what we're doing at BlueSpec and with customers with respect to RISC-V. So we've been working off and on RISC-V stuff for, I would say now, 2.5 years, really, when we first started playing around with writing some pieces for components of RISC-V. And what's evolved out of all of that is a kind of a integrated development environment. And so what we're trying to do is to provide this environment as a sort of starting point, a baseline for customers who have some specific value add that they're trying to do. They're trying to do some extensions, or they're trying to do some accelerators, or they're trying to do some their own RISC-V CPU, but they want the rest of the SoC out of the box, or vice versa. They're happy to take an existing CPU and want to do something special on the SoC side. They want to do software development on RISC-V, et cetera. So the idea is to have an out-of-the-box system that's ready to go, which is easily substitutable with various other pieces. So the customer can sort of focus on the delta that they're trying to bring forward. So I've shown 2 boxes below which show sort of the component side of things, which is there's a CPU, there's various components like MMUs, caches, and so on. I'll give a little more detail about all those components in a moment. And the second box is really about the verification environment that ties these things all together. So the cool thing about the BSV language in which all of this is written is BSV has extremely strong and parameterizable and elastic interfaces, which is really what enables being able to substitute and replace and pieces of what's there out of the box with pieces that might be useful for you. So as a very concrete example, we are currently engaged in a project with Draper, and the next talk after mine is actually a half-hour-long talk in which Andre Dehon is going to go into it in detail. So I won't go into detail, just to point out that, as you can see, there's lots of extensions involved. There's components to be added to the pipeline. There's tagging to be added to memory, extra CSRs. Tagging has to be propagated through the memory system down to all the way through the interconnect fabric into the memory system, et cetera. And of course, system software support has to be added to all this. So by using our baseline, essentially you start with an already running system that's already capable of booting Linux and focus on just adding this extension. So by using this, we essentially started the project in middle to late September. And expect to be able to produce our first untethered demo running on an FPGA board next month. So what are the components? So the CPU we have is called Flute, so called because it's a pipeline that makes mellifluous music. And from an architectural point of view, there's nothing fancy about it. It's a very straightforward 6-stage in-order pipeline with branch predictor, et cetera. The key thing is it has very clean interfaces between stages, so it's actually quite easy to shrink or expand the pipeline, and it's exploiting the elasticity of BSV interfaces to be able to do that, and written in a style that enables that. It has direct interfaces for GDB control, and I'll say a little bit more about that when I show you the environment in which it runs. So you can use standard GDB for interacting with the SoC, load an L file, run it, single step it, et cetera. The other key interface is the tandem verification interface, by which we are able to run the implementation and online check it against a reference model to make sure that the architectural state changes that it's causing are according to the reference model. So that interface has been very cleanly defined, independent of what's inside the box. So you could substitute in your own CPU there and exploit all these infrastructure features around it that allows you to connect to GDB and tandem verification and so on and so forth. As part of the Draper project, we've also added general support for tag data throughout the system. which is parameterized so that you can leave out tags if you don't want tags, but you can always add them if you want. As I said earlier, the key thing about BSV is this very powerful interfaces that are written in a very data flow style and a data flow semantics so that it's very easy to shrink and extend the pipeline depending on what you want to do with it. Other components, MMUs, the MMUs basically supporting the SV32 and SV39 virtual memory systems, the reference 30 bits, etc., support for super pages. The caches, even though the pipeline itself is an in-order pipeline at the moment, there's a lot of things that are partially going towards an out-of-order implementation, which we will, I'm sure, do in the future. Such as doing out-of-order caches, out-of-order TLBs, concurrent pipelines for integer, floating point, and memory pipelines, and so on and so forth. We also provide, as part of the overall environment infrastructure, what we call the ideal memory system. So if you're trying to identify bottlenecks in your CPU pipeline itself without the noise that comes from your memory system not being perfect, this gives you a setup by which you can focus on those particular issues. More components, an interconnect fabric that's parameterized in terms of number of initiators and targets, so you can plug in various things into it, supporting bursts, out of order accesses, and so on. A memory controller to connect to things like DDR3, DMA engine, and we are starting to populate it with a few devices. Our first few are likely to be things like, we already have a UART device by which we can do console I/O, etc. And we are close to getting flash and Ethernet devices as well on the interconnect. So this is a picture of the development environment, which is probably the key value in this whole thing, which is so I'd like to take a little time to go through some of the pieces here. So on the right, the yellow box is the SoC. It's the RISC-V CPU plus your interconnect plus your memory, etc. That represents your SoC. And on the left is, I've shown a host machine. The right-hand side box can either run in simulation or can be run on certain standard FPGA boards. And BSV has over the years BlueSpec has built over the years pretty rich connectivity between hosts and FPGAs, so it's quite easy to, very easy to bring up new stuff on an FPGA, add additional communication channels, and so on and so forth. So, so let me talk about a few things here. The GDB interface is essentially standard GDB, in this case RISC-V GDB, that talks through instrumentation that we have built on the right-hand side that has direct access into the CPU, into, first of all, the architectural state. So you can have standard GDB interaction with the CPU, including loading ELF files, running them, single-stepping them, setting breakpoints, and so on and so forth. The tandem verification I've shown here in two separate boxes. One is shown on the left-hand side, one is shown on the right-hand side. And I've labeled it A. And for example, on the right-hand side, the CPU, I've labeled it as B. This allows us to do an online A-B comparison between the implementation, which is the B box, and your model, which is the A box. And you can plug in various things. So we have standard interfaces and standard APIs around these boxes so that you can plug in various things out there. So for example, on the A box, one of the reference models we support is Spike, which means modifying a few modifications to Spike so that it can be controlled from this environment so that it stays in lockstep with the implementation on the right. We also have our own ISS, which is called Scissor, C instruction set simulator for RISC-V. We have a BSV model, which we call BlueRox, which is basically an ISS-style coding of RISC-V, but written in BSV. But being written in BSV, we can also synthesize it. And so you see that BlueRox can also show up in the A box shown on the right-hand side. That is, it can run on the FPGA alongside the implementation itself. Or you can plug in your own RISC-V CPU model. And at the moment, there's one other model that has been tried there, which is a formal model written in the L3 specification language by Prashant Munkur at SRI. And on the right, you can, of course, have your implementation like Flute or your own CPU if you can fit into that interface spec that we've provided. Or you might even use it while developing new versions of your model, comparing an old model against a new model, et cetera. So this environment allows you to quickly run a full system, focus on substituting on just the pieces that you're interested in, and run applications and even run OS code. So here's a screenshot of what you see in that environment. So on the right-hand window there is where we are running the simulation of the CPU, if it's a simulation. And if you're running on an FPGA, it's running behind the scenes on the FPGA, and this is the host-side proxy for whatever's running on the FPGA. And the whole environment looks exactly the same, whether you're running in simulation or whether you're running something on an FPGA. There are two console windows shown here. This window is the HTIF, the standard HTIF console thing, which comes by default when you start off with RISC-V. But we have also added explicit UART devices, and that's shown on the top middle of the screen out there. The smaller window at the bottom middle, which says GDB stub, is just a process that mediates between GDB, which is the left side window, and the running system on the right-hand side window. When I say mediates, what I mean is that GDB, when you run it in remote debug mode, has a so-called RSP, remote serial protocol, that's running, essentially runs ASCII text commands back and forth over some transport. And what the GDB stub does is it converts that into an appropriate communication that goes either to the simulator or to the FPGA in a packet-based format. But other than that, we don't actually touch that bottom middle window. And on the left, you're just seeing that it's just a trace of actually connecting to the system, specifying an L file, loading the L file, setting a breakpoint, running it. And when you run it on the top middle window, if you can squint, you'll see Hello World coming out over there. That's where the console I/O comes in. And then it hits the breakpoint. You can do GDB commands like list, do source level listing at the breakpoint position, and so on and so forth. So the environment, this is what the user sees, but behind the scenes is basically what I showed you in this picture out here. These are all just console windows giving you access to the various pieces out here. So that's basically it. Just to summarize again, what we provide is something that is out of the box, runs with that fairly rich environment that you just saw, runs RISC-V code both in user and supervisor mode, runs system privilege mode, operating systems, etc. And what our customers are doing with this is using that as a baseline from which they are innovating their deltas that's important for what they're trying to do. Thank you. I'll stop there.
What kind of performance do you get out of the continuous tandem verification?
Not very good. I don't have a specific number. Since you're running in lockstep, you're of course limited by the speed of that. So there's two levels of speed. One is just the fact that you're running in lockstep itself, however fast you can go on that. Now, the other thing is when you're running with an implementation on FPGA and the verifier on the host, then you might also be limited by the bandwidth of your communication, because, so what we've defined is a standard, as part of that standard interface is a packet format for each RISC-V instruction, which says for each RISC-V instruction, what kinds of deltas to the architectural state would we like to check. Because that is pretty small, even though the overall state change when running a program could be arbitrarily large. per instruction. It's a small packet that goes across, and that's basically what we're sending across. Nevertheless, you'd be bandwidth limited. So that's part of the reason why we also do synthesizable models. The idea is that you can run those models on the FPGA adjacent to the implementation itself, provided you can fit them both in, of course, and then you get rid of the bandwidth limitation. But you will still be limited by the model speed, which being a model is unlikely to run very fast. But we'd still expect even that synthesizable model to run at single-digit, low double-digit megahertz speeds. Yeah, it's certainly orders of magnitude faster than doing anything on the host.